So good morning, everybody, and welcome to the first seminar of the Astronomical Institute of Charles University in this semester. I will leave the technical details for the discussion or for the time after the discussion, and let's now turn directly to today's contribution, which will be about terrestrial planet formation, and the speaker is Brož from our institute. So please, Mira, the stage is yours.
Okay, thank you very much for the brief introduction. I'd like to first welcome our beloved ghost, which is the black screen. You know, in Zoom presentations, you often talk to a black screen. So this is my friend already, and I'm glad that she is here. So the first part will be devoted to a very brief introduction of problems we started with. Of course, I do not have time to present a throughout review of literature. I'm sorry for this, but let me mention at least these three basic problems. First, let me show some classical n-body models for terrestrial planet formation taken from Chambers and Weatherill, 1988 already. This is a pure n-body model with no gas, no friction, no dissipation, just n bodies. As you can see, it's n equals roughly a few hundreds, maybe in more recent model, few tens of thousands of bodies, which mutually interact gravitationally, and they can first create planetary embryos, which arise from the so-called isolation mass, which is a very well-known concept of the three-body model. And these embryos are always formed from a local material, which is local at a given heliocentric distance. The time scale is roughly 100 billion years or so, as you can see on this snapshot. This is the major axis versus eccentricity. And you end up quite often with four major bodies and two problems. Two major problems are that often, way too often, Mars is big and also Mercury is big. And as you can see here, the separation between Venus and Earth is roughly 0.5 AU, while the real separation is only 0.3 AU. So I'm kind of afraid that you remember me showing these figures in the past and talking about terrestrial planet formation. So today I'm going to discuss totally different scenario. The next step is this advanced ground tech model. It's actually about how giant planets affected the formation of terrestrial planets. What you can see on these snapshots, again, semi-major axis versus eccentricity, are giant planet, actually, these are giant planet cores initially, which accumulated quite a substantial amount of gas, and this gas is missing in the protosolar nebula, so that there are gaps around Jupiter and around Saturn. And actually these two gaps during the migration, which is called type 2 migration, overlap, and this creates a very unique situation. And the unique situation is that because the masses are different, the migration rates are different, and these two major planets can be captured in the 2-to-1 mean motion resonance, which totally changes the migration physics, because you are captured, and as a result, which I explain in physics of the solar system lectures, is that the migration is outward. And this creates a sort of inward and outward migration cycle, and it depletes the terrestrial zone, which can be seen here, because of course, the vicinity of Jupiter creates a lot of scattered material, and you end up with sufficiently small Mars, which was the biggest, well, the most important motivation for this model. Unfortunately, we again have big Mercury on the inner side of the terrestrial zone, and it's a model which is, as you can see, very popular in meteoritic community, because it separates It often separates the outward and inner part of the solar system. You can see the blue and red bodies, right? They are not mixed totally with each other. And it's popular because you can keep isotopic anomalies in the solar system as they are observed in meteorites. Number 3 is this Lambrecht and Johansen work from 2012, for example, which discusses a new dynamical mechanism, which is the pebble accretion. Pebbles are small size objects which are affected by aerodynamic drag during the existence of the gas disk, and they can be transported essentially across the whole disk. So immediately you see the advantage, right? You can form stuff from non-local material, and potentially your reservoir is much bigger than we thought before. Moreover, if you look closely at the vicinity, in the vicinity of a forming protoplanet, I think this is something like 3 Earth masses, right? These pebbles are deflected well within the Hill sphere, and they can be actually pushed by aerodynamic drag to accrete, which greatly enhances the cross-section for accretion. So it's a great mechanism because you essentially can accrete from the whole Hill sphere, which would otherwise be totally impossible. So that's enough for now, because otherwise we could discuss many other interesting things like opacity transitions, pressure bumps, and also convergent zones, especially for the outer solar system, where Jupiter is thought to be formed in a convergence zone due to the opacity transition related to the snow line. But that's not the topic of today's lecture. What I would like to discuss with you is a model which is for the terrestrial zone. So let me first admit that not all of the discoveries I'm going to discuss and are type 1 discoveries. These are like we have discovered something entirely new, right? Sometimes the discovery is of the type 2, which is like a feeling that I finally understood something and I no longer feel so stupid. That's actually the first case, right? The first case is type 2 for sure. This is a very well-known view graph showing infrared excess, or to be more precise, it's the percentage of stars within clusters which exhibit some infrared excess. And this is the time, actually the age of the cluster. And what is usually done, right, is that, okay, you fit it with an exponential, right? These are a number of well-known clusters, Taurus, Camelon is one, etc. And you fit it with an exponential, and you say, okay, this is a typical time scale of a disk, of a gas disk. But I think this is not true. It's simply not true. Right? First, there are certainly old disks. For sure, this is only a percentage. So it means that 50% stars, for example, for this Camelonis 1, can be older. Moreover, there are clearly some outliers. For example, this Eta Camelonis cluster, which is at 8 million years, and it still has 50% of stars exhibiting a strong infrared excess. So it's clear that there are outliers and all disks. And finally, I discussed this with Fedele during the last DPS meeting. There are also field stars, not members of clusters. And these were not surveyed. So we don't know whether they have disks or not. So it's a general question whether we can think of the solar system disk that it must have been exactly the average one. For sure, this is not true. Right? It can be easily older than 10 million years. Now, another question which I discussed a lot with my colleague Nicolas Dauphas, he's an expert on radiometry, right? And this is a brief sketch taken from, I think, Cruyer et al. 2017, which shows generally two distinct classes of meteorites, which are called carbonaceous chondrites from the outer part of the disk, and non-carbonaceous chondrites, shown in red. And what you can see here, these blocks are essentially their formation ages, right? Formation time, measured from 0, which is the formation of the calcium aluminum inclusions. Right? This is very precise measurement in several meteorites, which shows 4.567 billion years ago. So this is after CIA, and what you can see that first irons were formed, and then these stony meteorites were formed, and I think at 4, maybe at 5 million years, everything is formed or rained out. But this does not mean necessarily that gas is not present, right? Because gas can be still present, although it's depleted in these solids, right? In fine-grained dust, but it may still exist. So our idea was to test how the terrestrial planet formation behaves in case you have a gas disk. And this is the most, I think, promising model we invented. It's the model with the surface density which was inverted in the inner portion of the disk. It's in direct disagreement with the minimum mass solar nebula, which is the classical model by Hayashi. It's no longer valid, right? Because you have this non-local source of material. So that's our motivation for introducing an inverted surface density profile. We think it can be created by several mechanisms like MRI or active layers or disk winds. Although we do not treat these mechanisms in detail in our model, what we do is that we introduce viscosity as a function of R. And this viscosity controls this profile, which looks like essentially like this. It's inverted in the inner portion and then decreases in the outer portion of the terrestrial zone. So, in order to model it properly, including the pebble accretion, including these opacity transitions, we constructed, actually on the Chrenko constructed, a hydrodynamical model which treats gas on the left-hand side and pebbles on the right-hand side as two fluids. It's quite a substantial modification of Fargo. So just for reference, I'm not going to discuss the individual terms in our equation set, but what you can see here that we treat gas, pebbles, and of course protoplanets in the system. And of course, what you can expect that, for example, these pebbles are affected by gas drag, which is essentially this term, and of course its back reaction is treated in the equation of motion for gas. So I think we treat a lot of things self-consistently, at least in 2D, right? This is a 2D model where we assume that the vertical extent of the disk is in hydrostatic equilibrium, but the protoplanets, of course, they move in 3D, because if they have inclined orbits, they can miss each other and etc. So this is just for reference. And these are profiles we tested. That's what I talked about. This is the minimum mass solar nebula, the original model. This is the inverted profile. We can also see the temperature, the vertical scale height, or the aspect ratio in the third plot, and the respective opacity in the top plot. Of course, it depends which opacity you assume, right? There are a number of prescriptions, and I hope we used quite a new and updated opacity tables, because they are really important, right, to describe all the pressure bumps and all the transitions which are possibly present in the terrestrial zone. So I think this is from Zhu et al. 2012, which shows, I think, 13 regimes in opacity which are treated implicitly in our code. So what we do is that we start with already quite massive protoplanets, and classically we start with Mercury-sized bodies in the inner portion of the disk and Mars-sized bodies in the outer portion of the disk, because this mass range is usually determined by local growth of material. Now this can be also shown animated figure. As you can see, there are always some spiral arms, and this is the so-called Lindblad resonance, which drives these spiral arms. And what can be seen in detail if you really focus on a single planet is also the so-called corrotation region, which I'm gonna to probably show here. So this is another figure. It's the azimuthal coordinate from 0 to 2 pi and radius on the vertical axis, right? And what you can see are the sigma perturbations, right? Not the profile, but only perturbations. And then the streamlines. The planet is located on a cross. It's located here. And as you can see, it really perturbs and affects the gas flow in the vicinity. And what we see here as closed streamlines are the so-called corrotation region, which also determines the direction of migration. So that's the second mechanism we treat in our model. And finally, we also included the heating torque, which is essentially this mechanism. You have a planet here, then the gas is generally slower, and you have a headwind of gas going like this in the vicinity of the planet. And if the planet is heated, for example, by accretion, by differentiation, or whatever, then it radiates infrared heat, infrared radiation, which essentially expands the gas, and you have an underdensity just behind the planet. And of course, because there is underdensity, it means that this part, which is not perturbed, pushes the planet forward and prevents inward migration. So this is the third important mechanism included in our model. So that's essentially prediction, how it could work. It's the so-called migration map on the left-hand panel. It's essentially mass versus distance, and using color, we show dA over dt, or the migration rate, how fast the orbit moves in some major axis. So this is the transition we imagined, and what you can see if you simply extrapolate these dA over dt's, you see immediately that orbits can converge. And this is very useful for growth, for accretion, for merging. So that's why we proceeded and why we constructed other models, namely simplified n-body models with migration. Of course, it would be natural to treat it everything in hydro, right? But it's really difficult, especially when you have to deal with the inner edge of the disk. It takes months to compute sufficiently long integration, even on 100 CPUs. So that's the reason why we introduced this simplified n-body model, which, of course, this is the acceleration on the left-hand side, and on the right-hand side, these are the terms related to migration. So this is the classical prescription for changing the semi-major axis, right? And this is actually the function of the convergence radius and the time scale. Then we have these, this is the Heaviside step function, because we damp eccentricities. You know, eccentric orbits create waves, which in turn suppresses the eccentricity, pushes them to zero, but not exactly to zero. And this is a very important ingredient of our model, because we have some forcing in our model, which is called hot trail forcing. This is parameterized by this E hot. And similarly for inclinations, right? This is essentially the same. So that's nice, but you know, the number of bodies in our original model was only 28, the number of protoplanets we start with, and it's clearly a stochastic system, which is a bit unfortunate, because at first when you run a single model, it's essentially useless. You have to run 50 or better 100 models to understand the statistical outcome. And that's what I'm going to show here. That's one of our very successful realizations, where you can see the initial conditions on the bottom side of the plot, some matrices, and this is time coordinate. Maybe it's even better in an animated form, just the same stuff in black and white. Well, you can see that the orbits converge towards 1 AU, as exactly as prescribed. Now, they are, of course, if you push something closer to each other, the protoplanets start to perturb each other. They sometimes exchange orbits. They sometimes merge. Sometimes they even can form co-orbitals, like co-orbiting Earth with Venus, right? Or proto-Earth with proto-Venus. That was a tiny interval when you saw a co-orbital of a Mars-sized body with the Earth, but it was broken up later on. And finally, at about 10 million years, you end up with something, you can easily end up with something which is very similar to our solar system. In this case, there are 5 planets, and I've got a reason for this. But most importantly, right, the separation between Earth and Venus can be easily 0.3 AU or less, simply because these objects are always pushed towards a convergence radius. All previous models have problems with this, because if gas is gone, then there is always a repulsion. And this repulsion means that orbits diverge, and they usually end up at 0.5 AU, which is way too much. All right, another very natural outcome of our model is small Mercury as well as small Mars. Because if you have a convergence zone like this, right, of course, small objects remain at the boundaries of the convergence zone. There's no question about it. It's very, I think it's really trivial, right? And what does it mean? It essentially means that we no longer need any external mechanism to deplete the terrestrial zone. It's really in direct contradiction with Brož et al. 2011. Now, of course, we have our own problems, and one of the very serious problems is the overgrowth. When you have high pebble flux, which is usually measured in Earth massive area, right? Mass of objects which enter the terrestrial region in the form of pebbles, if it's too high, it's usually denoted n pebble dots. Units. If it's too high, everything in the terrestrial zone grows too much, which is demonstrated on the left-hand side when you can see something like 30 Earth masses or whatever. So I think it's clear from our modeling that the pebble flux must have been quite low, or at least short in time. Otherwise, everything would form something like mini Neptunes or hot Neptunes in the inner solar system. Now, if you are in a gas disk, it has several important implications. These are not detailed models, right? We are actually going to work on or chemical models related to Mercury, but we have not yet published work on chemical models. But what I can say quite confidently is that if Mercury is formed in a hot gas disk, then you can easily create its iron core simply by accumulating material which is close to the evaporation line of iron or magnesium-rich silicates. And it's very different because now we are not confined to a very narrow ring of material, which is close to the evaporation line, but we have a distant source. These are the migrating pebbles, because they can simply move inwards, they can evaporate in the course of their flight, and they reach the location of Mercury. So it's, again, in direct contradiction with models of Benz or Reufer and Aspel 2014, because mantle stripping by collision is no longer needed. This is actually a demonstration of this, how the temperature profile reaches the evaporation temperature. According to our tests with modified chemical composition, it can also extend the range of temperatures and consequently the range of radial distances in which Mercury could have been formed. If you increase the amount of iron, of course, it shifts the iron evaporation line elsewhere towards higher temperatures. It's logical because you have different gas pressure or iron vapors gas pressure, and there is a larger separation from these enstatite and forsterite minerals, which would eventually form silicate mantle. But we focus on this range of temperatures. All right, so one fact about Mercury, and another one, which we realized later on, Mercury is surprisingly a planet with volatiles. It's not, these are not, of course, water or these highly volatile elements, but it's very rich in moderately volatile elements. For example, in sodium, sulfur, or chlorine, as you can see on this plot, it's really rich. And it's actually quite logical if the disk at later stages, not the formation of Mercury, but at later stages, is colder, and it's always in these models that the disk is colder, it may be so cold that evaporation lines are shifted inwards, and you can deliver volatiles in the form of pebbles quite easily by inward migration. Another contribution might be the so-called late veneer, which is a delivery by planetesimals, but in this case, they would have to be scattered from the outer part of the disk towards Mercury, which is quite difficult. I think that delivery by volatile-rich pebbles is easier. Well, the same might hold for the Earth and water. Unfortunately, there are at least two problems, right? Why this is not straightforward. As I said, a late stage disk is cold, and the evaporation line of water can be easily inward 1 AU, right? So it's possible in principle, but these ice-rich pebbles or water-rich pebbles may be blocked by Jupiter, which creates a so-called pressure bump beyond its orbit. So essentially prevent the migration by this pressure bump. And we are now thinking how to overcome this barrier in the outer solar system. Now, second, how much water you have to deliver. Of course, you have to deliver at least one Earth ocean, which is in terms of mass 2.3 times 10 to minus 4 Earth masses. It's a tiny amount of total mass, But actually, because there is almost certainly some water contained within the mantle of Earth, the total number might be 2 to 8 Earth oceans, according to Peslier et al. 2017. So it's possible, but the pebble flux must not be too large, as I explained in the past. Probably it can be only a transient period. It's sufficient, for example, 10,000 years and flux like 2.2 times 10 to minus 5 Earth masses a year. It would be sufficient to deliver a substantial amount of water. But we again would have some problems with isotopic signatures. It's again a topic for a different lecture. So just if you would like to discuss isotopes, I would love to discuss with you later on after the lecture. So there are also some alternative theories, but as I tried to explain in this figure, they are not always successful. All right, now a few more important implications. What we also realized that in late stage disks, which might have been depleted, they have generally lower surface density. You can increase the eccentricity of Venus and Earth by means of the hot trail effect up to the current values of Earth and Venus. So I was really surprised by this. It works like this, right? You simply start with circular orbits. This is for Venus, and this is, we actually had not the fully formed Earth, but it's a half of Earth as planet. And if you embed it in a gas disk, what you see is an increased oscillations in radial distance, which corresponds to an increase of eccentricity, quite comparable to the current eccentricity of Earth. Right? It's a mechanism which was discussed by Ondra Chrenko in the past, which is related to formation of giant planet cores. But in this case, I was really surprised that you can explain it like this. Right? And what does it mean? Of course, it means that you no longer need some external perturbation acting on the terrestrial planet region, which was often used in the past to explain excited eccentricities of Earth and Venus. So that's one important ingredient add-on. Now, this is a sort of a brief summary that in a gas disk, you can actually gain some favorable situations because, you know, current orbits of planets are detached from each other. They do not cross each other. They are well separated. Right? Normally, in classical models, this can be only done by mergers, which means that you have an orbit and another orbit which crosses your orbit. And after a merger, there is always a jump in some major axis, like for example, like this. Sorry. And you have a jump in some major axis during the collision, which can detach you from the orbit which previously was interacting with you. So that's a classical mechanism. In our case, we also have a differential migration in a gas disk because different planet and different mass means different migration rate. And we also use eccentricity damping. So from high eccentricities, you can simply be pushed down to smaller eccentricities. And it's great, I think. I actually performed 2 very simple tests on Mercury's orbit and Mars' orbit. For example, if you imagine a fully formed Venus, like this one, right? This is Venus Mars object, and Mercury, which experiences a single one close encounter with Venus. What you can see is that you can easily push the eccentricity of Mercury up to 0.14 in this small set of simulations. And it's quite comparable to the observed eccentricity, which is 0.2 in terms of the oscillating eccentricity, but these are essentially oscillations. The proper eccentricity is 0.16, which is quite comparable, right, to the scattering of Mercury on Venus. And Venus then can migrate outwards because it's a more massive planet. And as you saw on the migration maps, these more massive planets migrate faster, and you can detach the orbit of Venus from Mercury simply by pure migration and nothing else. And essentially the same stuff is true for Mars, right? You can scatter it on Earth size or even smaller. I think I used 0. Earth object, and you can scatter it to higher eccentricities. Very simple and straightforward explanation for Mercury and Mars orbits. Unfortunately, it seems that it's not possible to create 4 planets at the end of the gas phase. And the reason is, of course, it's a stochastic model, so it's not a rule that you must end up with 4. Right? This is a histogram, number of planets versus number of simulations. You can end up with 5, possibly 6, which is the bulk of the probability distribution. On the other hand, it's also needed that you have a late collision. It's a quite complicated argument, but it's based on a geochemistry and the so-called tungsten anomaly. It's essentially this radioactive decay, right? You have hafnium-182, which decays first to tantalum and next to tungsten. And you can measure it in the Earth mantle and express it as this epsilon, right? This epsilon value. The difference between tungsten and hafnium is that tungsten is strongly siderophile, so it sinks to the Earth core, and hafnium is, on the other hand, strongly lithophile element, so it tends towards the mantle and eventually the crust. And what we measure here is the number of tungsten atoms which were created by this decay in the Earth mantle or the crust. And this is a very important information about the formation of the Earth and formation of the Earth core. Because at the time of this formation, all tungsten which existed at the time had to sink to the core. And tungsten we observe in mantle is only because of this decay, which is time dependent and short-lived, and consequently we can measure directly this Earth core formation. The observed value is this one, and what you can see in our modeling, right, if everything happens within 10 million years, as usually, right, all planet formation is finished within 10 million years, then this anomaly strongly increases up to the value of, I think, 10 or 12, which is totally incompatible with the observed value. And we need quite a substantial impact, I mean, moon forming impact, at about 45 million years, which is later. And that's why we prefer models with 5 planets at the end of the gas disk phase. And it's closely related to this. When you have these migrating orbits, right? It's quite common that collisions occur also for half-Earth versus half-Earth objects. These are called, let me say, non-canonical collisions. And in the past, it was thought that in order to form our moon, you need 0.9 Earth mass collision with 0.1 Earth mass collision. This is a canonical impact. It's no longer true, according to recent modeling with rotating Earth and etc. And we actually prefer a collision of half Earth with half Earth, which have several advantages. They are as probable as canonical invariants. Finally, a few notes about the space in between, right? Just let me recall that we discussed a convergence zone for the giant planets, and then another convergence zone for the terrestrial planets. What does it mean for the space in between? It must have been a divergent zone. Right? And that's the current location of the main asteroid belt. So we think, and we actually agree with Bertram, Witch et al. 2014, when they explicitly mention that the snow line, which was located in the middle of the main asteroid belt, probably, is actually, and its vicinity is a divergent zone from which bodies drift away, either towards the terrestrial zone or towards the giant planet zone. It can be shown on these migration maps, and it's actually also contained in our models, although we did not compute model for both from the inner and outer disk together. So there are some misalignments, but this is the terrestrial zone aspect ratio profile. This is the main belt aspect ratio, and there is some shift, and eventually there is giant planet zone aspect ratio. And when you have a dip in aspect ratio or the bump in aspect ratio, it means that there is always either convergence or divergence of orbits. It's very useful because first, according to our tests in the main belt, you can force the big planetary embryos to migrate away, and it actually corresponds to a mass depletion by a factor of 100 or so. So I think it's, again, quite a logical explanation why the asteroid belt is so low mass and so depleted, because everything migrated away from it in a gas disk phase. Second, you know probably that orbits in the main belt are inclined. They have a large spread of inclinations. But it's all, again, quite logical. If you have these massive embryos shown on some major axis versus inclination plot, so if you have these embryos, there is always some redistribution of inclinations. Like more massive bodies remain closer to the midplane, and low mass objects and these asteroids shown by crosses, because they are very small, right? Much smaller than these protoplanets, they are always pushed to higher inclinations. So that's another reason why asteroid belt orbits are inclined. Of course, we have the gas disk, but which would damp the inclinations back again. But of course, we checked gas drag acting on these highly inclined orbits, but it's sufficiently low that after 10 million years, you do not push these orbits back downwards to zero inclinations. And finally, two possible problems, or maybe possibly also advantages, I don't know yet. The inner portion of the main belt is dry. There are S-types asteroids, an S taxonomical class. Now, if you have these migrating pebbles, possibly also icy pebbles, which accreted on Earth, and we imagine they formed the Earth ocean, how could it be that the inner part of the main belt remained dry? I think it may be a natural outcome of the pebble accretion, because it's very efficient if you have a sufficiently massive seed or core in the middle. It's shown on this review figure from Ormel 2017. This is a low mass, a very low mass object, and you have only a slight deflection, right, of orbits, and you have accretion only if you hit exactly the central object. Now, if you are more massive, then you scatter and you have increased cross-section simply because there is some more deflection. But what is important here, that starting at about, this is probably quite close to Ceres mass, right? The largest asteroid, or as we probably should say, the largest dwarf planet in the main belt, you enhance its cross-section only if you are massive enough. And that's the likely reason why planets could accrete, but asteroids could not accrete these icy pebbles. And finally, there is some possible relation. It's for me, I think it's a more speculation, but what if Venus was dry all the time from the very beginning? We always thought, from my childhood, we always thought about Venus as being very similar to Earth, right? I was taught about the greenhouse effect, about runaway greenhouse on Venus. But just imagine, what if the snow line was located at 0.8 AU, temporarily? Then all material inwards at 0.7 AU was dry, and possibly it might be an explanation for the missing oxygen problem. Because if the Venus was wet, you have to evaporate water, of course, because it's dry today, but it's easy to remove hydrogen, and it's not so easy to remove oxygen. Because oxygen is not present in the Earth atmosphere, in the Venus atmosphere today, it's called a missing oxygen problem. Cassefier et al. Or Gilman talk about a strong solar wind and probably ion capture, which drove all oxygen away, but maybe it's simpler than this. So, by the way, I think yesterday there was a Nobel Prize announcement about in physics. Two of the guys are studying climate systems on Earth. So in order to understand Venus, I would say we would need similarly sophisticated climate models for Venus, and we should probably wait for another mission to Venus, which is actually upcoming. And finally, I'd like to thank a few grant agencies, especially Sherpas, which supported us during many hours we spent in Boulder, Colorado. So thank you very much for your patience. Thank you.
And we thank you for your talk. Are there any questions? At least on Zoom. That's what I can see. You can use those yellow or blue hands, or you can send a text message, or you can shout. Pavel Kroupa, please.
So if I just understand the model, just as a recap, you suggested the inner region had a lower surface density. This leads to a convergent flow near the Earth, and that would also help with the Mars-like body collision with Earth making the Moon, right? Is that a fair summary? And if that is, which I think is really nice, then why would one have a smaller surface density in the inner region? Would be then the question. I don't remember hearing a reason for that, but there probably is.
For sure, there are at least several possibilities. Unfortunately, at that time when we wrote our paper, we did not have a self-consistent model which would show the temporal evolution of the disk, and from 0 to, let's say, 10 million years. Today, I've got at least one, which is kind of simplified, one-dimensional model, which is easy to compute over 10 million years. And it seems that there might be either magneto-rotational instability, but for this you would need quite high temperatures in the inner portion of the disk. That's one idea. Another one is disk winds. Disk wind is initiated usually by irradiation from the sun, and the young sun might be especially efficient because it's strong UV source, much stronger than today's sun. So what we imagine is that the atmosphere of the disk was irradiated by UV and it essentially photoevaporates. This might create the inner portion of the gas disk to be depleted. The third possibility, and it's actually kind of secret, right? I should not talk about secrets when there are so many people, but what I think is another possibility is a sort of unstable inner part of the disk. When you have a suitable opacity transition and the magneto-rotational instability transition, which is essentially a viscosity transition, you can have a pulsating inner portion of the disk, which is a similar mechanism as, for example, in Cepheids. Right? It's a pulsating object which pulsates all the time because you power it with stellar radiation. So if it's this case, you can have depleted averaged profile in the inner portion of the disk.
Yeah, that's very nice. So you should disk around 6,000. If solution of the observation would allow that sort of observation, right? So you can actually test this model.
If I understood your question well, it was a bit
we
difficult.
Can't.
But you talked about observations, whether this can be observationally confirmed or rejected. And of course, I would love to, but it's the problem that you have to observe the disks at sub 1 AU scale, sure, which is not yet observationally constrained, right? What we observe with ALMA is usually the outer portion of the disk on the scale of at least several AUs. They observe, for example, the CO snow line, which is located in the outer portion at several tenths of AU. And another problem is that another possibility would be visible images taken by VLT and sphere instrument, but they are sufficiently sensitive only for brighter stars. What you usually see is the inner edge of the disk. I mean the very edge of the disk, which is strongly irradiated by the sun. And I'm not certain whether you can constrain the surface density profile again at this sub-AU scale. But you are definitely true. It should be tested observationally on exoplanet systems, taking into account that our solar system is probably and likely not the average one. And we have to look for outliers, definitely.
Okay, thank you. Yeah.
Not at all.
Is there any other question?
Of course.
Eric, when you mentioned these clusters and infrared access, is not that possible in principle that in that case, Epsilon Cameronis, I think you mentioned that it's old and there is still large excess, that its excess is coming from some material which is in between us and the cluster?
Yeah, sure, I can repeat the question. Petra asked, I think quite a skeptical question, whether the infrared excess for the outlier cluster, Eta Cameronis, right, whether it cannot be caused by essentially absorption in interstellar medium in between, if it's not ready.
Or some unrecognized another object on the way in between us.
Right, but I think that these observations are essentially resolved observations. We should probably check together, right? But I think these are observations of individual stars, and it's a matter of seeing infrared excess, which is somehow related to the star itself. You would need something like a hot cloud in between. Right? Of course, it's not cold interstellar matter in between, which is much colder. Right? I think this infrared excess is more like maybe even 100 kelvins. The vicinity of the star, not 30 kelvins, which is typical for cold interstellar matter. But we should check carefully, probably. Okay, thank you. So any other questions or comments?
Pavel again.
Yeah, thanks. But he's disappeared now.
He's still there. You can talk.
Yeah, sure.
Okay, hello. Yes. So I thought your suggestion that the snow line is closer in, further out, right? So Venus formed dry is very sensible. I think it's really a nice suggestion. Do you have a and why would you now? But why would one think that the snow line was further out? Because that's what you would have to. Is that again because the sun was much more active? Like, is this? He suggested that the early sun was very active and it would have just dried out the inner region. Possible?
Yes, so let me just try to repeat your question, although the transmission was again kind of unstable. The question was why the snow line should be always located at, or at minimum, at 0.8 AU. How is it related to the activity of the sun? Right? Probably Michal is expert on the sun and possibly also its past activity. So I think it's essentially unconstrained by observations of the sun itself today. We can observe solar analogs, right? So if we believe that all G2 type stars with the age, which would be today G2 type stars are the same, then we can rely on the observation of these solar analogs. And it shows that they are very active early on, and there are, I think, 2 or 3 possible pathways how they can evolve. They can remain more active for a longer time, or they exhibit a lower activity during their early evolution, right? Definitely not all stars are the same. And regarding the snow line, I think it's not very intuitive that, you know, the concept of equilibrium temperature, right? The equilibrium temperature is simply the equilibrium between incoming irradiation and the outgoing thermal radiation, which in vacuum can be computed very easily, right? It's simply 1 minus albedo times the cross-section, squared times the flux, which is the left-hand side. And on the right-hand side, you have something like 4 pi r squared, or possibly some epsilon sigma t to the 4th power, and you can express the equilibrium temperature. Hot disk, an early hot disk, is for sure much hotter than this, than the current equilibrium temperature, and it can be easily 1000 degrees, right? And on contrary, if the disk is colder, you are shadowed from the sun, and the temperature in the cold later disk is lower than this one. But again, I'm afraid it cannot be a rule. It cannot be computed from first principles. I mean, the temporal evolution, right? Because it depends on too many objects: the sun, the disk, its viscosity, viscosity is, by the way, one of the major heating mechanisms in the inner portion of the disk. And as a result, I'm afraid that we again have to tune our models to fit the terrestrial planets as we observe them, including their geochemistry. And that was likely evolution of our gas disk.
Thank you. It's really very nice. Thanks.
Thank you. So if there are no other questions, I think we spent already 1 hour or so.
So anything on the Zoom?
I see no hands, just one animal. But
There is some question in the chat.
I see. So let me check it out. I see a common question from Michal Křížek about Newtonian mechanics and causality. What I would say explicitly is that Newtonian mechanics is a suitable limit of the general relativity, which we can safely use within the solar system, maybe with the exception of Mercury. So I'm quite confident. I'm much less confident in my simulations in terms of stochasticity, which is inevitable. It's a very simple consequence of an n-body problem, which is inevitably stochastic, right? If n is not many orders, like many thousands or many millions, like in statistical physics, then you cannot treat a single model as the outcome. You always have to discuss, similarly as in statistical physics or in quantum mechanics, you have to discuss the probability distribution of results, as I hopefully did with my histograms of the number of planets versus the number of simulations. But that's really common in our business. All right. So thank you very much. Thank to all of you who came in person. I see, maybe. Okay, so that's just we discussed this with Michal in the past, but it's great to discuss it again. Okay, thank you very much and see you. Goodbye.